So a subspace of a vector space and as usual we'll call our vector space V. A subspace of a vector space V is a vector space that lives inside it. So it's a vector space U which is contained in V. And so the standard notation for that is this one right here. So this means that U is a subset of V. So in other words, a subspace of V is a subset that happens to be closed with respect to the axioms of addition and scalar multiplication, and which contains the origin. So let's see. For example, if V is any vector space, so these are just basic trivial examples. Then 0 and V itself are always going to be subspaces. Okay, so those are like the most uninteresting examples you could have, basically. So so the idea is that if U is a subset of V, then the operations of addition and scaling will be defined for this guy. And those operations, since V is a vector space, those operations are automatically going to satisfy most of the parts of the vector space definition. So if you are dealing with a set that is contained inside a vector space, then you only have to check 3 things. And so that's the content of proposition 134. So suppose that V is a vector space and that it has a subset U. Then U is a vector space if and only if. And so, well, yeah, let me just finish the sentence here and then I'll come back and explain. So if and only if we have that it contains 0, it's closed under addition, and it's closed under scalar multiplication. Okay, so just backing up a little bit to this symbol here, I just wanted to explain that this is read if and only if, because it's the arrow going both directions. In a definition, I will write this as the if with two F's, just to indicate that I'm defining something. In a theorem, however, I prefer to write it as an arrow pointing both directions. It means the same thing, but it's just to emphasize here that it's a statement which needs to be proved in both directions.